everyone. We are honored to have Dr. Taeil Kim here to give us a presentation at the virtual platform from the University of Wisconsin-Madison. So Dr. Taeil Kim, he's a principal nuclear engineer at Argonne National Lab, and he's also the principal investigator of the sodium-cooled fast reactor safety experiment project. Dr. Taeil Kim got his PhD degree from the Korea Advanced Institute of Science at 2012. Now his presentation today is about the fuel relocation process for the sodium-cooled fast reactor. And to speak will last 40 to 50 minutes, and we will have time to ask questions at the end of the presentation. Now let's welcome Dr. Taeil Kim.
Hello, good afternoon, everyone. Thank you for introduction, Dr. Wang. My name is Taeil Kim from Argonne National Lab. The subject of my presentation today is metallic fuel relocation experiment with pressure injection in a pin bundle core structure of a SFR. So, okay, so the outline of my presentation is as follows. First, I'll give you a brief introduction about our experimental project. Then I'm going to show you our experimental facility, including test section design and experimental procedure. Then I'll give you some of our previous experimental research with using our experimental facility. Then I'm going to show you our latest experiment of fuel relocation experiment with pressure injection, which is Rpi1. Then I give you some conclusions and talk about a little bit of our future work. So let's start with introduction. Argonne National Laboratory and Korea Atomic Energy Research Institute agreed a cooperative research and development agreement, which is CRADA, to perform safety experiments in the area of fuel relocation behavior in severe accident conditions to support prototypic generation 4 sodium-cooled fast reactor, PGSFR, in Korea licensing process. There are a lot of studies already have been conducted regarding this fuel relocation behavior in case of severe accidents. The best example is actually EBR1 meltdown case, which can be an evidence of fuel disperser in case of severe accident in SFR. And this picture shows the EBR1 meltdown core after decommissioning. And also, there are a lot of studies about fuel fragmentation behavior in a sodium pool geometry. And most of these studies show that relocated fuels have a high porosity. This picture shows fragmented fuel, which was conducted in Argonne in 1970s. The porosity of this fragmented fuel is up to 90%. So high porosity means this fragmented fuel can be cooled automatically. However, there are very limited data available for the metal fuel relocation behavior in a core structure, realistic core structure. Therefore, the goal of this CRADA is to develop database of the metal fuel relocation behavior in a realistic core geometry. Therefore, in Argonne, we built this experimental facility to conduct metal fuel relocation experiment for our argon carrier CRADA project. With this experimental facility, we have conducted two types of experiments previously. First one is a single-pin metal field relocation experiment to investigate this metal field relocation behavior in a narrow sodium annular channel. Then we moved on to pin bundle metal field relocation experiment, PBR experiment, to investigate the metal field relocation behavior in a more realistic pin bundle geometry. So after successfully conducting these two types of experiments with our metal field relocation experimental facility, we found that in case of actual severe accident condition in SFR, there will be a pin plenum overpressure is expected inside the fuel cladding because of the fission gas buildup and bond sodium vapor inside the fuel claddings. So, which is actually beneficial for fuel dispersion and fuel fragmentation. So in the present study, the metal fuel relocation experiment was conducted with a pin bundle test section under more prototypic conditions by injecting the metallic fuels into the coolant channel with the pressure. So this is the introduction. Now let me introduce our experimental facility. This figure shows the schematic diagram of our experimental facility. It mainly consists of pressure melt vessel, where the uranium is heated to target temperature inside the graphite crucible here by induction heating. And the test section where the relocation, so uranium injected into the test section and relocation occurs inside this test section, which mock up the fuel assembly design of the PGSFR. And the sodium transfer system for supplying sodium into the test section and removing sodium vapor created by during the experiment. So in previous experiment, we used this melt vessel for our previous single pin relocation experiment and pin bundle relocation experiment. And this vessel can be only pressurized to 15 psi G at 300 degrees C. Then we upgrade this vessel to pressure melt vessel to have a pressure injection capability up to 100 psi G at 500 degrees C. And this slide shows the test section design of pressure injection experiment. The total length of the test section is about 0.7 meter. It consists of 7-pin fuel claddings in a hexagonal array. The cladding material is HT9M steel. So actually this test section design is based on the fuel assembly design of PGSFR. So cladding diameter and cladding material and pitch between the fuel claddings are same as PGSFR fuel assembly. And we use a wire wrap spacer to spacing each of claddings. And sacrificial boundary was fabricated on each of the claddings to fuel can be injected into the coolant channel easily. And alumina filler was filled inside the claddings right below the sacrificial boundary. So when uranium was injected into the inside the claddings, it stops here and then injected into the coolant channel. These 7 claddings are contained inside hex can, and sodium is filled near to the top of the fuel claddings. And there is an upper plenum for release of relocated fuel and sodium vapor. And we used guided structures such as transition funnel and diverter to direct uranium into each of the claddings. So this red area is the injection path for the injected fuel. Once it reaches to the sacrificial boundary, the sacrificial boundary is broken instantly and then injected into the coolant channel and then relocated to the downward or upward. And on the right side figure, it shows how uranium is injected from the pressure vessel to the test section. First, uranium is melted and heated to the target temperature inside the graphite crucible by induction heating. Once temperature is reached to the target temperature, then we pull this plug by using a pneumatic cylinder. Then molten uranium is dropped into the injection line. This molten uranium reaches to the rupture disk between the pressure vessel and the test section. This rupture disk is melted down instantly by this molten uranium, and because of the pressure difference between the pressure vessel and the test section, uranium is accelerated and injected into the test section. And this slide shows the test section design of previous experiment. In the single pin relocation experiment, obviously we use just one single fuel cladding, and around the fuel cladding we used a zirconia tube to make a narrow annular channel. The gap between this single cladding and zirconia tube was about 1 millimeter. And in the pin bundle test section, we used 19 claddings in the pin bundle test section, and we used a guided funnel to direct uranium into the 7 central pins so that uranium can be injected into the claddings and then relocation occurs. But in this previous experiment, we dropped uranium just by gravity, and there was no pressure difference between test section and the vessel. And this slide shows the experimental procedure. So first, we heat the transfer system and the test section to 200 degrees C to avoid any solidification during the sodium filling process. Then we transfer sodium from the sodium supply tank to the test section by pressurizing the sodium supply tank. Once sodium is transferred from sodium supply tank to the test section, we heat the test section to 700 degrees C or the target temperature by using a split tube furnace around the test section. After then, we start to pressurize the pressure vessel at room temperature to 20 psig. Then we started heating the uranium fuel inside the crucible by using induction heating to target temperature. And as uranium heated up, the internal temperature of this pressure vessel also increased as well, and pressure is gradually increased to 50 psig, or target pressure. Once uranium is reached to the target temperature, we pull the plug and drop the uranium into the injection line, and uranium reaches to the rupture disk. Rupture disk is broken instantly, and then uranium is injected into the test section. And the uranium is accelerated by pressure difference between the pressure vessel and the test section. So this is our experimental procedure. Now I'm going to show you some of our previous single pin relocation experiment research and pin bundle relocation experimental research. without pressure injection. So for the single pin relocation experiment, this table summarizes the experimental condition of each single pin experiment. We conducted 3 sets of single pin experiment, and the fuel temperature inside the crucible was varied from 1522 degrees C to 1690 degrees C. And sodium temperature was varied from 460 degrees C to 1622 degrees C. Also, we increased the fuel amount from about 100 grams to 300 grams as the experiment proceeded. And these pictures are the post-test radiographs of each single pin experiment. And you can see the disruption of the fuel claddings due to the eutectic formation between the fuel and the cladding. The extent of the eutectic formation increased as fuel temperature increased and sodium temperature increased and fuel amount increased. And also, some of white circle voids are formed by sodium boiling, and you can see the white voids inside this post-test radiographs. This is formed when uranium is breaching the cladding and entered into the sodium channel, and sodium was boiled by this hot fuel. And here in SPR3, which has the highest fuel temperature and highest sodium temperature, with the highest, the most uranium amount used in SPR3 experiment, the disruption of cladding, the top portion of the cladding was mostly gone by the eutectic formation. And the outside zirconia tube was broken because of the vigorous sodium boiling and the eutectic vigorous sodium boiling, and probably the summer shock between the temperature difference between the uranium fuel and zirconia tube. So it was broken, and some of uranium got out of the annular channel and frozen outside of the annular channel. And we found a lot of fragmented fuels in this SPR3 experiment, which can be attributed to the sodium boiling. And this slide shows SPR2 experiment SEM analysis. So this picture shows the disassembled test section of SPR2 experiment. You can clearly see the disrupted fuel claddings due to the eutectic formation. We cut the sample as shown in this picture to have SEM images of each sample. So this picture shows the cross-sectional view of each sample, and on the right side, SEM images of each sample is shown. To the right direction, inside these SEM images, the magnification is increased. So obviously, sample number 2, where the disruption occurs, showed most eutectic formation formed in the sample. So these white regions are eutectic, formed between the uranium fuel and the HT9 cladding. So sample number 1 to 3, it's hard to recognize the original fuel cladding shape. But as getting further from this disruption area, for example, number 4 sample, you can see the shape of the original cladding. And from the SEM analysis, the cladding was almost consumed by eutectic formation, and eutectic is very close to the end of the cladding surface. And sample number 5, which is furthest from the disruption area. It shows clear boundary between the cladding and the fuel, which means no utility formation, not much utility formation occurs. Actually, we found very interesting things in this number 5 sample. The initiation of utility formation was captured in this SEM. You see this small circular shape of the eutectic, and it is invading the cladding area. So from this single pin relocation experiment, we found that eutectic formation is the cladding rupture mechanism, and fuel can be injected into the narrow sodium channel through this eutectic formation and can be fragmented in a narrow sodium channel. So after single pin experiment, we moved on to the pin bundle experiment, which has more prototypic fuel assembly design. And so this table summarizes the experimental condition for pin bundle experiment. In pin bundle experiment, we try to maintain experimental condition as close as possible compared to single pin experiment. So fuel temperature in crucible was varied from 1652 degrees C to 1687 degrees C. And sodium temperature was varied from 635 degrees C to 686 degrees C. Fuel amount was around 800 grams. So these are the post-test radiographs after each PBR experiment. And this is the pre-test radiographs of the pin bundle test section. So in PBR1 experiment, as you can see, we didn't use a guide funnel, and we just dropped fuel into the top of the claddings. So some of uranium actually dropped into the coolant channel directly, and some of uranium entered into the claddings and then breached the cladding by utility formation and entered into coolant channel. Because of that, because the pure uranium has higher freezing temperature than eutectic between uranium and cladding, so it quickly frozen near the TC3, and the penetration or dispersion of this uranium was lower compared to the other experiments. So most of uranium found to frozen near TC3, thermocouple 3. Whereas in PBR2 experiment and PBR3 experiment, we used a guide funnel to direct uranium into all of uranium into the inside of claddings, so that uranium can only be injected into the coolant channel via the eutectic formation between the cladding and fuel. So the injected fuel was not pure uranium, but uranium cladding eutectic, which has much lower freezing temperature. The freezing temperature of the pure uranium is 1132 degrees C, and the freezing temperature of the eutectic is around 725 degrees C. So injected uranium uranium iron eutectic can flow further than PBR1 experiment to the thermocouple 6 and thermocouple 7. And we also found the top of the cladding portions are mostly consumed by the eutectic formation, and we couldn't find any left structure after the experiment. So after PBR2 experiment, we would like to try to localize the injection of the fuel into the coolant channel, so that we coated yttrium oxide internal surface of the cladding to limit the amount of the eutectic formation. But still, the injected uranium, the fuel was the uranium iron eutectic, so still the fuel can flow much further than PBR1, but slightly shorter than this PBR2. And in PBR experiment, after each experiment, we also measure the pressure drop across the test section to indirectly measure the blockage of each test section. So by measuring this pressure drop, we can indirectly estimate the porosity and pore size of the relocated fuel. So for the PBR1 experiment, it shows highest pressure drop values compared to the other pressure drop, the other pin bundle test section. And PBR2 shows the lowest pressure drop values because it has largest amount of information, so that uranium can be dispersed furthest. And in PBR3, the pressure drop values are in between these two. And also we analytically calculate the pressure drop value and compare this calculation value to the measured data. And by comparing these two values, we can estimate the porosity of the relocated fuel. So porosity of the relocated fuel was varied from 0.2 to 0.3 for PBR1. PBR2 has highest porosity of 0.5 to 0.6, and PBR3 shows in the middle range of porosity between PBR1 and PBR2. So from this PBR experiment showed that the relocated fuel has porosity and does not completely block the coolant channel, even in case PBR1. So that means this relocated fuel can have cool-over geometry after relocation inside the core structure. So these are the previous experimental research, and after the completion of the previous experiment, we moved on to the pressure injection experiment, as I explained earlier. So after we upgraded our facility to have a pressure injection capability, we first would like to verify new injection mechanism works with this new pressure vessel. So we conducted a copper injection test first with exactly same transition funnel and diverter and fuel claddings, which will be used in the main experiment. So this picture shows the experimental setup of the copper injection test. This is flange and transition funnel, diverter, and cladding portion. And we put a crucible around this test setup to catch injected copper inside the crucible. And we put an insulation around it to limit the splashing out of the copper out of the crucible. The amount of copper used in this test is around 424 grams, which has similar volume of the uranium that will be used in the main experiment. And this slide shows some of copper injection test research. So this is a rupture disk. The rupture disk is completely melted along the edge of the top flange. And the internal surface of top flange and the transition funnel is coated with thin copper. And we didn't see any large chunks inside the transition funnel or the flange. That means uranium was injected smoothly through this test setup. And as you can see here, some of copper was found outside the surface of transition funnel. That means the injected uranium was bounced back and levitated to the transition funnel. And continuing the copper injection test, this is the diverter and claddings after the test. a lot of frozen copper was found outside the surface of diverter and claddings. And many copper fragments found inside the crucible. The size of this fragment varies from less than 1 millimeter to more than 1 centimeter. And these large chunks are actually stick to the surface of the internal surface of crucible. So that means when copper was injected into the crucible, it splashed to the surface of the crucible. These many fine fragments can be attributed to the higher ejection velocity due to the pressure difference. So from this copper injection test, we confirmed that this new pressure injection mechanism works for our main experiment, and we moved on to our main experiment. So again, this figure is our test section design. Consists of 7 cladding pins. And this table summarizes our Rpi1 experimental conditions. So fuel material is uranium metal, and cladding material is HT9M steel. And fuel temperature inside the crucible was 1706 degrees C. And the injection pressure was 54 psig, and sodium temperature inside the test section when uranium was injected, it was 712 degrees C, and fuel amount used in the Rpi1 experiment was 790 grams. So this is the result of Rpi1 experiment. First graph is temperature change inside the crucible during the experiment. And second graph is temperature measurement inside the test section. So TC1 is located at the top of the cladding. TC2 is located near the sacrificial boundary and top of the alumina filler. And each of the thermocouples are apart about 2 inches distance. And 0 second in the graph means the moment of uranium release inside the pressure vessel. So once uranium is released from the pressure vessel, the temperature seems still going up because we didn't turn off the induction coil. So graphite crucible is also inductive material, so it can be heated a little bit, but after then we shut the power off and temperature decreased very quickly. And this temperature, unfortunately, during the experiment, TC1 was broken during the experiment, so measurement of TC1 is not available. But for TC2, the blue line in this graph experienced a very sharp temperature peak right after few seconds after the uranium was released from the pressure vessel. So it experienced a sharp temperature peak and then increased to its maximum temperature and then gradually enter into its equilibrium state. TC3, which is the solid red line, did not experience a sharp temperature peak, but experienced a sudden temperature increase and then gradually increased to its maximum temperature and gradually enter into its equilibrium state. So this abrupt temperature change means very hot uranium was reached to these thermocouples. And TC4 was also did not experience this type of temperature change, but it gradually increased to its equilibrium state. However, the TC5 to TC9 from here to here did not experience any noticeable temperature change over the course of the experiment. That means rhenium probably did not reach to this region. So from these temperature behaviors imply that some of injected uranium froze near actually TC1 to TC4 and did not reach TC5 to TC9. This was a bit surprised because we expected, because of the pressure injection, we expected fuel could be flowed further than our previous pin bundle experiment. But we found the region in the next slide. So this is the picture of the transition funnel after disassembly. So same as the copper injection test, the rupture disk melted completely along the edge of the flange. And the internal surface of flange and the transition funnel was coated by rhenium. Thin rhenium layer was found on the transition funnel. And no large chunks of rhenium was found inside the flange or the transition funnel. Also, we found frozen rhenium outside of the transition funnel. That means rhenium was actually injected and then levitated to the upper plenum region, to the top of this transition funnel. And one more, this picture shows the inside of the test section after disassembly, and this is the diverter, which is this part. And as you can see, inside of the diverter was not plugged in our main Rpi1 experiment, but in case of copper injection test, some of copper was actually plugged this diverter. That's because in the copper injection test, we didn't hit the test setup, and test setup was sitting at room temperature. But in our main experiment, we heated the test section to 700 degrees C, and the heat loss during the injection process was probably much less than this copper test. That's why rhenium can be completely injected into the coolant channel and relocated to the downward or upward. And as you can see here, many frozen rhenium found inside this, outside of the diverter, which is the upper plenum region. This is the evidence of the levitation of injected uranium to the upper plenum. This was the reason why uranium was not penetrate deeply into the downward, but most of uranium was actually bounced back to the and levitated to the upper plenum region. This is important in SFR severe accident scenario because removal of the fuel from the core region can be a negative reactivity feedback effect, so that SFR can be safely shut down in case of severe accident. So this was what we found from what we learned from the Rpi1 experiment, and actually we were planning to have a X-ray radiograph after this disassembled test section. However, due to the COVID-19 situation, we had to pause our experimental work. So, and recently, actually, we got confirmation that X-ray operation can be resumed. So soon we are going to get the radiograph of this Rpi1 experiment and see how uranium is dispersed inside the test section by using X-ray machine. So yeah, this is the Rpi1 experimental research, and now let me move on to the conclusions and future work. So our previous experiment, which is single pin relocation experiment and pin bundle relocation experiment without pressure injection, showed some evidence of dispersion and fragmentation of the injected fuel in a realistic core geometry, not in an open pool sodium geometry. Then, then we conducted a copper injection test, which confirmed that the new injection mechanism of the new pressure vessel can inject fuel into the coolant channel at high speed because of the pressure difference. So in Rpi1 experiment, the different temperature behaviors implied that some of injected uranium froze near TC2 to TC4 and did not reach TC5 to TC9. This was a bit surprise for us, but we found the reason why uranium did not penetrate deeper than previous PBR experiments. This was probably that a large portion of the uranium was levitated to the upper plenum region due to the pressure injection. And post-experiment examination confirmed that thin uranium coating on the flange and transition funnel, and no large chunks of uranium found inside the flange and transition funnel. It also confirmed that many of frozen uranium outside of the diverter and transition funnel. This indicated that the levitation of the injected uranium to the upper plenum. So we can conclude that in case of pressure injection, there is a possibility that uranium can be quickly removed from the core region, which results in the negative reactivity feedback effect for the SFR sodium crude fast reactor. The radiographic test was postponed due to the COVID-19 pandemic, and it will be resumed as soon as the Xray operation is approved, and which is already approved, so we will move on to the next step quickly. And in addition to that, currently our team, me and our team members are working on the construction of a real-time Xray video system to record the moment of fuel relocation inside the test section. So with this Xray, high energy Xray video system, we can see the relocation behavior in the real time. That is our next target, and the next RPI experiment is planned, which is RPI2, is planned with this real-time Xray video system. So let me introduce about this real-time Xray video system quickly. So Argonne purchased Linatron M3A, which is a high-energy Xray machine, which can create 3 MeV Xray energy with dose rate of 18,000 rad per hour at 1 meter distance. So which has a potential to record the fuel relocation motion inside this test section during the experiment. This can show us exactly when and how molten fuel is injected into the coolant channel, as well as the how and in what extent of fragmentation and dispersion occurs inside the test section. So this is the Xray machine that we purchased, and this is the schematic diagram of the real-time Xray video system. Consists of this Xray machine and test section and the detector panel and computer. So we can see the behavior of fuel in real time during the experiment. So this is the end of my presentation. Thank you for your attention, and any questions about the presentation is appreciated. Thank you.
Okay. Thank you very much for the wonderful presentation from Dr. Taeil Kim. So do we have any questions from the audience? I saw one from Mike Corradini. So what's the prototype range of the fuel met temperature and the mass and the sodium temperature? And these prototypic values are based on what model simulation? So you can see the question at the right side of your.
Yep, I can see the questions. Okay, so fuel melt temperature, that's a good question. So actually, in parallel, we are doing this experiment, but also our SAS code analysis group also developing this experimental model using SAS code, and there is a analysis about the PGSFR safety analysis using this SAS code, and they estimated the fuel temperature. It depends on the accident scenarios, but fuel temperature can be up to 1400 degrees C when it is injected into the coolant channel. And sodium temperature, that's a very good question. So they found some of sodiums are already boiled when it is injected to coolant channel. So temperature is already more than boiled temperature. But in some cases, sodium temperature is around 700 to 600 degrees C. And these prototypic values are based on what model simulations. So this model simulation means, so that's what we are using in the experiment. So the SAS code is the model we use in our experiment. Is that answer for you? Thank you. Yep.
Yeah. So I have another question. Is you mentioned that your tactic may change your temperature for the cladding and the fuel. So how much it could change this failure temperature?
You mean the yeah? So I mentioned quickly the pure uranium melting temperature is 1132 degrees C, but eutectic temperature of fuel and cladding is the freezing temperature can be lowered to 725 degrees C. So there is about 400 degrees C difference. So that's why it created a lot of difference between the fuel penetration in PBR experiment.
Okay. Thank you. And do we have other questions? So I have another small question is what kind of uncertainty did you concede during your experiment process?
Uncertainty. So obviously the instrumentation uncertainties are involved in the experiment. The uncertainty levels is around, I need to check it out, but it should be around less than 5%, I would say.
Okay, thank you. So if we don't have any other questions from the audience, oh, I got another one.
Okay.
So it's the pressure buildup that occurs to push the molten fuel downwards from the fission gas with fuel lots.
Okay, pressure buildup occurs push the molten fuel from the fission gases with the fuel. So in real fuel assembly, before fuel is disrupted cladding and injected into the coolant channel, inside the fuel there is a pressure buildup because of the fission gas and sodium bond vapor in this fuel assembly of the PGSFR or other SFR. So when it breaks the fuel cladding, because of the eutectic formation, the fuel is ejected into the coolant channel with a very high pressure. So that's why we try to have pressure injection capability in our recent experiment. But you asked about pressure buildup that occurs to push molten fuel downward from fission gas with fuel barrage. So okay, so I already answered. Okay, thank you.
Okay, so do we have other questions? So if there's not other questions, let's thanks again for Dr. Taeil Kim's presentation. Thank you very much. Hope everyone have a good remaining of the day. Thank you.
Yeah, thank you, everyone.
Thank you.